Okay. Shall we start?
Wait 1 second. It's setting up.
Okay.
Okay, now it's good.
Okay, let's start. So hello, everyone. Welcome back to our today's CFSM seminar. And today is our great pleasure to have one of our organizer, Dr. Zhen Li, as our today's speaker to introduce his work on the parallel in time model. So Dr. Zhen Li is now an assistant professor of mechanical engineering at Clemson University, and he received his bachelor in engineering mechanics from Wuhan University in 2005 and a PhD in fluid mechanics from Shanghai University in 2012. And after a short postdoc experience in University of California at Mercy, he joined the Crunch group at Brown University in 2013 as a postdoc and was promoted to research assistant professor in 2016 and a research associate professor in 2019. So his research focuses on multi-scale modeling for tackling challenges in multi-scale, multi-physics problems, in particular on mathematical and physical foundations of coarse graining, multi-scale methods, and machine learning approaches for applications in complex fluids, biology, and soft matter physics. Dr. Li has published more than 50 journal papers and released multiple open source software packages, including the MUI library, the user MISO GPU accelerated particle simulators, and the DPD meso module of LAMPS. So for my research group, we have a very good utilization of Dr. Zhen Li's open source software. And Dr. Zhen Li has devoted a lot of efforts and time to the development of the field. And I believe he is now a rising star in our community. So with that, let's welcome Dr. Zhen Li to start his talk.
Okay, thanks, Jiaoyan, for the very nice introduction. So today I will try to share some work in my group on how we can bridge non-temporal scale for multi-scale simulation using the parallel in time method. So this work is done together with my collaborators in Brown University and also Minnan in Johns Hopkins University, and also the Yusuke Hasegawa in University of Tokyo. So first, I want to introduce the outline. So today I will introduce the parallel in time in two parts. So the first part, I will introduce how we can use the supervised parallel in time to do the non-scale, non-time Lagrangian simulation. The second part, I will introduce how we can use the parallel in time to improve the neural network training. So let's talk about the motivation. So I want to, before we use the parallel in time method, I want to introduce what's the original motivation. We want to do the very long time simulation. So we can look at this fish. So this is a zebra fish. Okay, if you consider the zebra fish as the baby zebra fish at the very beginning of its life, so this zebra fish is kind of transparent. So people actually can, because it's transparent, people can very easily to see the vascular growth, or we call the vascular remodeling process at the beginning of the baby zebra's life. So we can see this phenomenon is at the very beginning. There's a lot of vascular network is kind of growing over time, and then later the vascular network were kind of optimize its efficiency to transport oxygen and have blood flow through this network. So people call this is vascular remodeling process. So we have a collaborator at University of Tokyo. they can provide the experiment data. They can observe the network, vascular network in the spring of the zebrafish evolve over time. So now we are talking about this process. So if we want to model the blood cell transport through the vascular network at the cellular level, so if we do the simulation, we can actually use explicit method to model how the blood cell flows through a channel or a vascular. But the time scale, because you are trying to capture the cell level details, so the time scale, even you use a supercomputer, the time scale you can reach is about micrometer, or the maximum you can go maybe is microsecond. The maximum time scale you can reach by using supercomputer, you can reach to the milliseconds. But if we look at the time scale for the real-time blood flow in the zebrafish and vascular network, one heartbeat, okay, we just consider one heartbeat, the time scale is bigger than about 1 second. If you want to model the process over multiple heartbeats, then this means your simulation time have to reach to seconds or minutes or even longer. But if you compare this time scale, you will see even you have super computer, you do parallel simulation, you cannot reach to the time scale, and it's kind of biological meaningful. So this is the motivation why we want to accelerate the simulation, the multi-scale simulation, include the cell level details to extend to long-time dynamics. So now we're talking about when we have supercomputer, usually the straightforward way we can do the parallel simulation is we do the domain decomposition. Domain decomposition means you have a system. We consider this the overall system. So if you have multiple CPUs or GPUs or many kind of processors, you want to do the parallel simulation, you just decompose the domain into small subdomains, right? So you put each subdomain onto different CPUs so that you can solve the subsystem on each CPUs in a parallel way so that you can get the speed up of your simulation. So now we will see the speed up and reverse respect how many CPU you are using. So we will see this red line. This red line is the speed up. So you can see at the beginning, if you increase the number of processors, you can have a speed up. But as you have more and more CPUs, and your subsystem becomes smaller and smaller, and actually then the communication between CPUs will dominate the computation, and then you will get a kind of parallel slowdown. This means if you have more CPUs, you actually cannot use the resource of CPUs, because your speed up, you use more CPUs, your computation time will be increased. That means you have a slower speed up. So this is a kind of a bottleneck of the long-time dynamic simulation. You cannot accelerate your simulation just using more and more computation resource. We just consider there is one example I want to mention is if you have a fixed system size, if you don't do the long-time simulation, the current state of the art is you have to run a very long time. For example, for this simulation, the authors spend 6 months perform 1 microsecond MD simulation on a supercomputer. So the reason they have to run 6 months, this is because you have the parallel slowdown. You cannot use more resource to try to accelerate this simulation. So I personally does not have patience to wait 6 months to wait simulation results. So what I'm thinking is if we can use some algorithm, we can accelerate the process. We can reduce the 6 months simulation to 1 week or several days. Then it would be great for me. At least for research, it does not have patience to wait 6 months to see the results. So, but as we mentioned, if you have a fixed system size, you want to run the long time simulation. If you just simply use domain decomposition, so then we cannot gain any speed up just by simply using more computer resource because there's a speed up, slow down, right? So then we will consider if we have this kind of blood cell flow simulation, how we can make the simulation faster to reach to the time scale beyond a second or 2 minutes or even longer. So then we will introduce the idea of parallel in time. Okay, the parallel in time method is trying to do the decomposition in time domain. For example, I want to run the simulation from t0 to a longer time, tn. Okay, so you know that the simulation usually you cannot skip the time scale because the time scale usually you need the initial condition of the system so that you can run the simulation. That's the reason usually in time is always serial because you have to start from T0 and run to T1. After you have the initial condition at T1, then you can run T2. So this is usually what happened for the domain decomposition. But when we want to do the decomposition in time domain, then we have to introduce 2 solver. Okay, so the first solver we consider is coarse propagation. Coarse propagation means you can use a very coarse solver, or you can. We consider the coarse solver is less accurate, but it can run very fast in time. Okay, so that means first you can run the coarse solver in time, start from T0 and run to T1 and T2 and T3, and you can run the entire time series use the coarse solver. And then you will have the initial condition for all the fine system. For example, the fine scale propagation is the solver you want to really solve. Now we will have the initial condition. We can obtain the initial condition at T1 and T2 and T3 from the coarse solution from the coarse solver. Then we can consider this is a prediction of the initial condition. It's not necessary this prediction should be correct, but if it's correct, then we can accelerate the process. If it doesn't matter is correct or not that accurate, we can use the initial condition obtained by the coarse solver to initialize the fine solver. Then you will see after we run the coarse solver in time, we have the initial condition for the fine solver simultaneously at T1, T2, and T3. So this means then we can, for the fine solver, we can use the initial condition to run the fine solver at a short time domain. For example, now we run the fine solver simulation. We don't need to run from T0 to Tn. The fine solver only need to run from T1 to T2 and T2 to T3. So this kind of short time simulation is run simultaneously at different CPUs. So we call, if you give an initial condition to the fine solver, the fine solver can realize this initial condition is not perfect. The fine solver will correct their solution to the true solution. So then if the one time correction is not enough, then we will do iteration. And eventually we can correct the solution to the true solution. And if it's converged, then all the time domain will converge simultaneously. So now we're briefly describe the power in time. Actually, this algorithm is a kind of predict then correct algorithm. For example, the n+1 time step solution is determined by the cost by the cost prediction plus a correction term. So you have a prediction and then I do correction. If the fine solver is stochastic, then we can expect that eventually the solution is stochastic. Okay, so this is the kind of workflow. You can this red subdomain is run serious in time, this course propagator, and you use this initial condition to run the fine solver at different CPUs, so that you use course solver to couple all the solution in time, and you run the fine solver as a corrector. And then actually, then we can, if you want to run very known simulation, actually we can use the mean field solver to supervise the fine stochastic solver in time domain, so that after converge, you will have the fine solution. So we just start from very easy example. We call this the pedagogic example because it's pretty simple. It have analytical solution. So we just want to prove this idea, use this example. For example, we have a deterministic ODE, okay? So the ODE is du plus A plus omega cosine omega t. So with the constant A equal to 1 and omega is pi, half pi. So we know this kind of solution have exact solution. So then we just if we want to use the power in time algorithm, we need to generate two solver. As we mentioned, we need a solver to predict over time, right? Predict the solution over time. So we use a very use a simplified ODE. For example, we just ignore the cosine omega t term. So we just use the du dt equal to A. This is a cost solver, okay? So we solve the cost solver in time from 0 to 10, okay? It's 1 to 10. But this cost solver will solve severely in time. And then we can use the prediction, the initial condition of the simplified ODE to initialize the exact ODE. And then we will have fine, because we split the time domain into 10 subdomain. So we have 10 fine solver for correction. So each solver will have a length of 1 time units, but this is run parallel in time. So then we will see what will happen, okay? So we have initial condition generated by the simplified ODE, and we use the exact ODE to correct the solution. So this is what will happen, okay? So at initial condition, for example, the first iteration, because you use the du equal to A, right? If you solve the cost solver, you will find you will get a straight line because it's du equal to A. So the cost solver solution is red line, and you use the initial condition at the different time instant time. For example, T1, T2, T3, you initialize the fine solver. You will see the fine solver is try to correct the cost solver solution to the true solution. So because this is one-time correction is not enough to correct the answer to the true solution, so we do another iteration. So you will find at the second time step, after the second correction, the blue curve looks much better compared to the true solution. And then you do another iteration, you will convert to the true solution. So this means you do the prediction and the correction, you are able to generate the solution in continuous in time domain. Okay, so for this case, we use 10 time subdomains, but we only need 2 iterations. The reason we need 2 iterations is the cost solver. We will see the cost solver is du equal to a. This is a very rough prediction, and this we need 2 iterations. But if your rough the cost solver is good, maybe you only need the first iteration, then you can converge to the true solution. Okay, so now we will show a movie. This is how the parallel in time is run. First, you do the serial in time, and you do correction parallel in time, and then you can correct the answer to the true solution. So this is the strategy. Because we generate the 10 subdomain, we only do 2 iterations. This means we can usually get 5x 5x speed up, right? As you have more and more subdomain, you will have better and better speed up for the parallel in time algorithm. So now we will consider another example. Is kind of a little bit more complicated. So we have a flow solver. We call this dissipative particle dynamic solver. You can consider this is a cost-gradient molecular dynamic simulation. So we can do some flow simulation, use the DPT solver. It's a very fine solver. But this is a high-dimensional ODE. It's very expensive, okay? So we want to run the DPT solver faster. Then, as we mentioned, if you want to drive the DPT solver in time domain, you need a cost solver. So we consider if you do the mean scale, mean field approximation of the DPT solver, you usually have the Navier-Stokes equation. So we use this mean field solver, Navier-Stokes equation, Navier-Stokes solver to drive the DPT solver. So what happened is we use NS solver to provide the mean field prediction UT to the DPT solver. We use the UT to initialize the DPT solver, so the DPT solver can do the correction for the solution. So we mentioned that the NS solver is compared to the DPT is very cheap. So we consider this is serial in time, and the DPT solver is very expensive. So this we run in parallel in time. This is the governing equation. You will see actually the 2 set of system have significant different governing equation. But as long as the NS solver can provide the mean field solution to the DPT solver, then we can use the DPT solver to correct the solution. Okay, so this is the idea. Then we want to introduce some operators in the macro-micro coupling. Okay, because we have the NS solver, this is the grid-based solver. So when you have the grid-based solver solution, we need to use the solution to initialize the DPT solver. So we need a mapping operator. This means you have a velocity profile, and you need to initialize all the particle velocity using the NS solver solution. So another operator we want to use is when DPT solver have the solution, you need to convert the DPT solution to the NS send to the NS solver. So that you need to do some average, because you are using the particle information to send to the grid information. So you need to do some projection operator. Actually, we usually do the average, and then you need a filtering, because the DPT solver actually generates very noise data. Okay, so if you send it to the NS solver, if the noise data is contained there, you have to consider how you can filter the noise. But the good thing is NS solver have the viscous term. If you consider the viscous term is the second derivative of the velocity. Actually, if you have noise, high frequency noise, the viscous term will naturally filter the noise generated by the DPT solver. So then for NS solver, we do not need to explicitly do some filtering, but this is the property of NS solver. So this is the workflow. So for example, at the very beginning, we need to run the code solver in time to generate the initial condition for the fine solver. Then we just do the filtering and using some average algorithm to send the correction, send use the DPD solver, use the NS solver solution to initialize the DPD solver to do the correction. Okay, after we have correction, we will project the solution to the cost propagator. It's NS solver. Then we do correction and we do prediction again. Then we do the iteration. Then we can correct the solution to the true solution. Then because we do iteration, we need to determine what is the termination condition. So the termination condition is we just consider the difference of two different iteration, and we require that the difference of two different iteration should be smaller than a tolerance. This C tolerance is a predefined parameter. For example, usually we use 1%. Okay, so there's because we need to do iteration, then we will consider there's if there's a guarantee, your iteration will converge to the true solution. So there's a theory prove that the parallel in time algorithm eventually they have theoretical guarantee your iteration eventually will converge to the true solution. The worst case is you have for example, you have n time domain. Then you need the n iteration. N iteration is the worst case. So that means you actually use the fine solver and start from the T0, run. If you run n iteration, actually the fine propagation will go through T0 to the Tn. So then the only thing is you do not have speed up, but there is a theoretical guarantee you will converge to the true solution. So now we will see how the results looks like. So before we talk about show the results, we want to introduce what's the strategy you want to increase the speed up. So we mark here K is the number of iteration, N is the number of subdomain. So the time parallel in time algorithm, the world time is determined by the K is the number of iteration. And in each iteration, the time cost is you need to spend one time for the fine solver. You need to spend n time of the code solver because you need to run the code solver parallel in time. So the serial, if you compare the serial method for the spatial domain decomposition, so then the time you are using is beta times n. N is the number of subdomain, and the TF is the time cost for each subdomain. So usually if you have perfect linear speed up, the beta should be equal to the 1/n, okay? But in most of cases, the beta cannot reach to the 1/n. Usually it's a number between 1/n to 1. So the worst case is that you do not have any speed up, so you will have beta equal to 1. The best case is beta have the number of 1/n. This is the best case. So if we compare the speed up of the parallel in time method, actually, if you can guarantee the beta is bigger than this value, then you will have the speed up. So now we will pay attention to the right-hand side term. Then we will find actually, if we want to make the right-hand term smaller, the only thing we need to do is we need to keep the tau c, the coarse propagator. It's much smaller than the fine propagator. Then you can have better speed up. So the reason we choose you have the NS solver compare the DPD solver because the NS solver if you consider the tau c for Navier-Stokes solver is kind of compared to the tau f is maybe 0.1% cost. So that's the reason we need to choose two solver. The time cost for the two solver, if it's the ratio is very large, then actually you have better speed up for the power in time method. Okay, so we mentioned this is determined. We said the speed up actually is determined by the number of subdomain n, right? So then if we have more and more number of subdomain, actually we have better and better speed up. But the problem is you actually cannot use much smaller time domain because there is a decorrelation process of dynamics. So if you have dynamics, if you compute the correlation function of your system, for example, this one I computed the momentum correlation of the flow problem, then you will find the correlation is decay over time. Okay, so that's mean, for example, if we want to make sure we have 1% or we want to have a very small correlation of the solution. So we need to consider you have to guarantee your dynamics if you select the time subdomain, because you need the initial condition, right? And you use the fine solver to correct the solution. You do not want the initial condition will affect your final answer. So that means your time subdomain have to something bigger than the decorrelation time of the dynamics. So for this problem, when we compute the correlation time, we found, okay, if we keep the time subdomain in the order of 10, we can guarantee there is no correlation in the momentum term. So we consider that the lower bound of the sub length of time domain would be 10. If the length of time domain is bigger than 10, then we can guarantee there's no correlation of momentum in the same sub time domain. Okay, so now we will see an easy example. Is this is a one-dimensional flow. Okay, so we have one-dimensional flow. We just consider your PDE Navier-Stokes solver. We use a very wrong viscosity term. For example, this is the 10 times viscosity. If this is 10 times viscosity, actually it's generate a wrong solution, right? So then we will see. We consider that the delta T is 10. Okay, the subdomain is 10. The cost solver, NS solver use time step 0.1. The DBT solver use the time step 0.1. Then we do 20 iteration. We can guarantee that 20 iteration, we can guarantee the power in time solution will converge to the true solution. So you will see at the 0 iteration, this is the solution. The solution is 10 times smaller than the true solution. But you as long as you do the iteration, you will converge to the true solution. Okay, so we will see after you converged, the velocity profile at different time, or the subdomain will converge to the true solution. And now you will see if we use 10 times wrong viscosity, you need to do 20 iteration. Now we will see what if we, this is the NS solver drive the DBT solver. So if we consider the L2 norm, okay, the reference solution minus simulation solution, we will see how the L2 norm is reduced over iteration. So you will see at the very beginning, actually for the earlier time, the error reduced very fast. And you will see over iteration, the L2 error of the solution will reduce exponentially. So after you have the 20 iteration, all the solution have very small L2 norm. And the good thing is, if we look at the L2 norm histogram, So because we know that DPT solver is our fine solver, we want to see if the fine solution contains the required stochastic fluctuation and their correlation. You will see as you do the iteration, the solution, the L2 norm histogram will converge to a normal distribution. This means our fine solution do contain the required stochastic fluctuation and their correlation. So eventually you will have a solution. This solution, the solution is converged to the true solution, and the solution also contain all the stochastic feature that are required for the DPT solver. Okay, so as we mentioned, if you use 10 times wrong viscosity, you will have go through the 20 iteration, and this is L2 norm. You will see this is log scale, so that you can see the L2 norm actually is decreased exponentially and fast over iteration. And then if you use a better NS solver, for example, we use 2 times viscosity, so then you only need 5 iteration, you will get correct answer. If we use the correct true viscosity of the NS solver, then actually you only need 1 iteration, you can correct all the solution to the true solution. So this is some information. If you have a very good predictor, okay, predictor solver, then you only need 1 or 2 iteration, you can correct to the right answer. But if you have a very kind of bad predictor solver, then you have more iteration. You have to do more iteration. That means your speed up will be sacrificed, but you can guarantee the solution eventually will goes to the fine solution, the correct solution. So this is the 1D case, and then we can compare what's the speed up. So we said we can compare the war time. We use a lot of processors. We can compare the speed up compared to the traditional spatial decomposition and the power in time algorithm. So you will see when you have the CPU is smaller than 128, actually the spatial decomposition have better performance, slightly better performance than the power in time algorithm, because in power in time we need to do iteration, and the spatial decomposition you don't need to do any iteration. But when we have more and more resource, okay, you will see the power in time will have better performance. So if you compare this one and this one, when you have a same simulation, so you use the 1024 CPUs, the power in time actually the speed up is 100. The time cost is half of the traditional spatial decomposition. So if we compare the efficiency you will see also, you can see this is the power in time will have better performance than if you have more and more computation resource, the power in time will have better performance than the traditional spatial decomposition. But the good thing is power in time is a totally different concept than the spatial decomposition. Actually, if you have a lot of computation resource, you can combine the spatial decomposition and the power in time algorithm, so that you will have twofold speed up. So that means if you combine these two methods, if you have more and more resource, you will run the simulation faster and faster. Okay, there's no speed up, slow down problem. So now we'll consider if you run the 2-dimensional flow. Okay, 2-dimensional flow, we use the needle driven cavity flow. So the NS solver, we use Reynolds number 600. The DPT solver, we use Reynolds number 200. So you definitely you will see the center of the NS solver, the vortex center predicted by the Navier solver is something wrong. But you will see when we do the iteration, okay, so this is a different time. You will see at some time there's two solver is try to DBT solver try to correct the vortex pattern predicted by N solver. And when we have 5 iteration, then the DBT solver actually can correct the answer to the true solution. So this is for the one-dimensional case and the two-dimensional case. Now we will consider the original case we want to consider. Okay, so this is actually that's our initial motivation why we want to do the power in time. We want to simulate the vascular the blood flow inside the vascular network. So this is what we did is we have an experimental collaborator. They can do the CT scan of the vascular network. This means they can do scan the layer by layer of the vascular network in a zebrafish, in the brain of a zebrafish. This is the structure that they actually obtained. Okay. Then actually we can use this structure to construct the DBT solver to simulate how the blood flow through this network. So we said we have a DBT simulation, but we need to run this simulation beyond 1 second. So we use a 1D blood flow model as our predictor. So this 1D model is very fast. You only have a flow rate through each section. And we use this solver to drive the DBT solver so that we can perform the power in time simulation. So as we mentioned, if you have an experimental image, so we have a method we can generate the DBT system directly from this image. So there's a method how we can do that. For example, you have an image, we just input this image in our system. We can directly generate a DBT system, and we can simulate the flow through this system in a straightforward way. So that means we have this kind of experimental image, then we can generate a DBT system. This is actually represented by the DBT particles. So we use multi-medium particles to represent this system. So to check if the solution can converge to the true solution or converge to some termination condition, we just random select. There's a 12 section. We consider the flow rate across that 1, 2, 3, 4. Here we have some other section. Want to check the flow rate. Okay, so this is a system. We have 1D model, we have 3D DBT model. Then we do the simulation. We check the flow through different this is our checkpoint. We have 12 checkpoints to check the flow rate. So you will see we can split the 1 second into 4 period, 4 subdomain. We run the simulation. We found over the iteration, eventually almost all the solution will converge to some constant flow rate. So we were think this will eventually converge to some true solution. Okay. So then after we run the simulation, we compare, we have the 3D model, this is DBT results, and this is the 1D model. And this, we can do the comparison. We can guarantee after converge, the flow rate at different part of the network will be consistent. Okay, so you can then, because you have the 3D DBT model, after you converge, you can check all the blood flow at a different location. You can see there's some aggregation, there's some pattern, and all the details were inside the flow simulation. Okay, so this is the first part we introduced. This is how we can use the power in time. You can actually accelerate the Lagrangian simulation to a very long time. The second part, I will introduce how we can use the same idea we use to train the new physically informed neural network. Okay, so very brief introduction of physically informed neural network is we are trying to encode physical knowledge (PDE) into a neural network training. For example, usually if you consider you have neural network, you have input. For example, you have X, T. You go through the neural network, you will have output U. But usually, if the U is some property, should certify some PDE, you can put this U in some constraint. For example, you can compute this is the PDE. The U variable should certify. Okay, so you can compute the residue of the operator U theta minus G. This is the residue of your solution. If you put the residue as the mean square error of the solution, and you can define a loss function, some part is from your neural network. This is actually based on some observation and boundary condition and the initial condition, but you also have the constraint for the PDE. So that means after you train this neural network, your solution will certify the observations, and you also certify the PD, the constraints. So people call this is the physical informed neural network. So then using the benefit to using the physically informed neural network, we call the PINN, to solve the PDE, you have a very obvious benefit is it doesn't matter how the PDE looks like. You solve the PDE, you just go through 3 steps. First, you define the neural network architecture. Then you define the loss function. And then you train the neural network using some optimizer, for example, other optimizer. Then all the PDE, you will just follow the same 3 steps. Then you can solve. It doesn't matter how the PDE looks like. You can go through the 3 steps to solve any PDE. Okay. So for example, if you want to solve this equation, so we go through the step. First, you define neural network. Then you define neural network, and you have to specify the architecture first. You define the neural network, and you define the loss function, and you do optimization. You can solve this equation. So this will be kind of a more easier or more general framework you can solve for different PDEs. Then we will see what's the challenging here. So we consider because the neural network, if you see the 3 steps, okay, you see the 3 steps. So the step 1 is very easy. You just define the architecture. The step 2 is to define the loss function. The only time-consuming part is to train the neural network. Now we will see what's the computational cost on training the neural network. So if you consider you have a DNA, the depth is D, okay? The data set is S. Actually, the training time is proportional to the S power 2 power D. So that means if the S is very large, the training time will be very expensive training. So now we'll consider if you have time-dependent PD, okay? The size of data set is proportional to the length of time. If you have a 2-dimensional problem, if you do the time-dependent problem, you have a 3-dimensional, and the time is very long, okay? Then if you have a long-time problem, the work on the large data sets directly will be very expensive. So we know that the training time is proportional to the S power 2 power D. So then we can consider if you can split the data into small data set, and you do the training over the small data set, and you use split the data, and you can use some method to connect the time-dependent solution. Then actually you can get significant speed up on the training of the neural network training. So now we'll see that exactly the same idea. So use a prediction. You use a coarse neural network as a prediction, and you use the fine neural network to do the correction. Okay, so this is how we do that. So coarse propagator will run serial in time, and the fine solver will run in parallel in time. So we introduce this simple example. So we have the simplified ODE, right? As I mentioned, we can use the neural network to solve this ODE. So we use a very coarse neural network to solve this simple equation. And we use a fine neural network, the bigger size of neural network to solve the exact ODE. So this is the solution we obtained. This will be very similar as we mentioned before. You use a correction, prediction solver, and you use a correction, and you can correct the solution to the true solution. So now we'll consider if you have the speed up. Now we'll consider if you have the fine pin training, because you need to do iteration. Actually, we found that different iteration, the time cost is quite different. On the second or third iteration, this will converge much faster than the first iteration, because the second iteration will use the pre-trained neural network you obtained in the first iteration. For example, for this problem, the second iteration only need about 4,500 ECOPs to converge. And for the first iteration, you need 11,000 ECOPs to converge. So then if you see the speed up, actually the dash line is the linear speed up. Then you will see you use probably in time, because you have the faster convergence over the second iteration. You can obtain the super linear speed up for this kind of simulation. So then we will consider, okay, this example is very easy. Now we will consider a slightly difficult problem. Is we have a nonlinear diffusion reaction equation we want to solve in a 2D dimensional domain. So we will see that diffusion coefficient in this domain is a function of the position. Okay, so this is a D0 exponential function of the concentration. So that means the diffusion is coupled with the concentration field. This is a nonlinear equation. So as we mentioned, then if you use parallel in time, you need a simplified solver as a coarse propagator. So we just use the diffusion coefficient is a constant. We just consider this D0. And we use this solution as a coarse solver. We use the exact solution as the fine solver. Then we run the simulation. We use a coarse solver. We use about 2,000 residue points to check for each subdomain. Okay, but for the fine solver, we use much number. For fine solver, we were trying to use different size, different number of subdomain. Okay, and we also consider the much more sampling data we want to do the data point to the training. And the convergent criterion we consider is tolerance of the MSE error is 1%. Okay, after you define the coarse solver and you define fine solver, then we can see, okay, the black line of this is reference solution. Okay, reference solution is obtained by very fine scale Nathan-Boltzmann equation simulation, and the red dash line is a solution from the parallel pin solver. You will see actually, after you run the first iteration, it's almost converged to the true solution. So that means the coarse propagator is given the very good prediction, so that you will converge to the true solution in one iteration. Okay, so now we will consider the computational efficiency. So we will see if you have a coarse solver, you use the coarse solver, use a network to do the prediction. Actually, the time cost is significant for the neural network crossover. And actually, the speed up we can obtain is about 5. Maximum speed up is 5. And that if the crossover we use an analytical solution or the final difference solver, and actually we can reach to 20 times speed up for the neural network training. So the good things is we will see here. So we know that if you have a small neural network, this is usually for the small data set. So we found actually the CPU, you train the small neural network, work on small data set. Actually, the CPU is 2 times faster than the GPU. Okay, so because using power in time, you can speed a big data set into small data set. Actually, then we can enable the use of CPU. Okay, because you only need to train the small neural network on small data sets, so that the CPU have better performance in GPU. And this will give the opportunity if people does not have a high performance GPU, you can still run your neural network training on CPUs at a very fast speed. Okay, so this is all my presentation. I'm very happy to take any question.
Okay, thank you very much, Jen, for this very interesting talk. I think you cover a lot of like fundamental development in terms of the parallel in time algorithm, and I think this is really a brilliant like idea. So if this idea can be really extended to multiple different application field, so the bottleneck of the time limitation can be solved like really in an efficient way. And so with that, I think we can open our discussion for the audience. If you like, if you have any question, please feel free to unmute yourself and ask your question.
Yeah, so if you have question, you can unmute yourself and ask your question. So Joanne mentioned a point is actually after we use the power in time, actually there is also have a lower bound of the time domain you can select. But as long as you have very long time domain you need to cover, actually if you couple the power in time with the combine the power in time with the domain decomposition, you actually does not have any limitation on the computing resource. How much computing resource you can use. Previously, for example, you only use the domain decomposition. Then if you have a fixed size of system, the maximum resource you can use, actually, if we go back to the very beginning of the parallel slowdown. So maybe here is the maximum computation resource you can use. If you use more computer resource, you will slow down your simulation. But now if you couple with the domain decomposition with the power in time, then actually you can get twofold speed up. Then if you use more computer resource, you will have better speed up.
Yes. So yeah, I think most of the audience are still like digesting the information. So there are a lot of information to think about. But maybe I can start to ask a question. So you mentioned like a serials, like a crossover, and also the fine, like a parallel in time, like solver. So you mentioned a lot regarding the iteration. So for example, when you do the a parallel in time for the Navier-Stokes solver and coupled with the DPD solver. So your time, like the physical time, will be determined by your Navier-Stokes solver. And when you move into your fine solver, the DPD part, so the iteration doesn't really count into the physical time part, right? I mean, how we should
Yes.
understand iteration? Like a DPD, we also do the time marching, right? But that time is more like a pseudo time, or so how we should understand the iteration?
Yeah, actually, if you consider the solution, if you just consider in the non-dimensional case, the flow problem only determined by the Reynolds number. So if you can match the Reynolds number, actually the solution is the same. So this means in each iteration, you are run from, for example, for this simulation, we run from the 0 to the maximum time is 320. So every iteration you need to run this long time. But because if we go to the very sample example, you will see because your cost solver cannot give you the correct answer at the very beginning. Okay, so you run the NS solver, it will give a very rough prediction, and you use the rough prediction flow field to initialize your DPD solver. Your DPD solver needs to spend, for example, one-time unit, one-time subdomain to try to correct the answer to the true solution. But because your prediction is very wrong, you cannot correct the answer to the true solution in one step. So that after you have the one correction and you will do the iteration again, you use the new data, okay? Use the new correct data to use the NS solver to run this again. So you will have, for example, previously, for example, we have T3, you have T2. The T3, the first iteration, you give the solution is come from the NS solver. It's pretty wrong. But on the second iteration, you are starting from here, right? For example, you are starting from here. You run a cost propagation. It will give a new initial condition. This initial condition combined with previous solution, you can somehow you can see the red is cost propagation, green is the fine propagation, and if you combine this together, you can get a better prediction of the initial condition. And then every iteration you have much better prediction than the previous iteration. So by doing this, you can correct the answer to the true solution. But in some case, if your fine solver, your cost solver is pretty good, you already give the initial condition just at the right point, then you only need to run maybe just a one shot, you will get the correct solution. As long as your predictor can give the solution very close to the true solution, then you don't need much iteration. We mentioned that at the very beginning, for example, we use we use a very wrong NS solver by purpose. We just use a 10 times viscosity. This means if you do the time-dependent solution at the first iteration, the NS solver give you this curve. You use this curve to initialize your DPD solution. Your DPD solution cannot directly get to the right answer. So it will correct a little bit, and you start from here to do the iteration. It will go a little bit. Usually it will try to every iteration, the DPD solver can correct a little bit toward the true solution. But your initial condition is off too much. This reason at the very beginning, we will see the iteration. If you use 10 times viscosity, actually you need a lot of iteration to convert to the true solution. But if you use correct viscosity, for example, 1x viscosity, then you only need to do one iteration. Because your prediction is pretty close to the true solution, you use that as the initial condition to initiate the DPD solution. Your DPD solver can directly correct this to the true solution.
I see. Yeah, that's really smart. So, right. So I think I really need to read your paper to see more detail, but the idea is really kind of straightforward and clear to me now. Yeah. So any other question from the audience?
Yes, I would have a short question. Thanks for the interesting
Yes.
talk. I was wondering about under which conditions you can actually achieve a speed up using this parallel in time method. You had one slide where you showed us this comparison of beta, so your domain decomposition scaling factor. Yeah, exactly this one. And you compared it to n times tau c, so n number of time slices times runtime of the core solver, and you have this tau c in the red box and talked mostly about it. So I see that it is a super important component, and we have to minimize it because we have to execute the core solver sequential in time, obviously.
Yeah.
But there's more here. There's also tau f, tau r, tau p, so the runtime of the projection, mapping, and filtering operations.
Yeah.
And maybe you could tell us more about these three parts.
Yeah. So this part is just you have two solver, right? You need to do the communication. So if you have a very good communication scheme to send the data from one solver to another solver, then it would be fine. But if your communication is not good, then this will may be time consuming. So for us, we have a coupling solver we call the MUI. So we have a library that take care about the communication between solvers. So we test that the MUI only takes about less than 5% of the total computing time. So it's you can consider this part. You do the communication between the two solver. If you have a very good algorithm, so this you can ignore this time cost, because usually this time cost is only happen when you do the communication. You run the simulation does not cost anything. It's one-time cost. But this this one is very significant, because if you, for example, before our work, all the power in time, they are trying to use the same solver. Okay. The only difference is you have a fine grid and a coarse grid, but the equation is the same. So that means you have the tau f, tau c at the same order. Maybe, for example, the fine solver is 10, the coarse solver is 5. It's not that significant. So that the speed up is totally determined by the key over n. And if you have n is actually, if you consider this is large, you need times n. Actually, you cannot get a good speed up. The reason we want to choose two different systems, we use the DPD solver. We do not solve the same set of equation, because if you solve a different set of equation, the time cost is significant, different. For example, if you consider the degree of freedom of DPD solver compared to the NS solver, is maybe the 3 order or 5 order difference. So we are trying to,
especially
we are trying to minimize, reduce this term.
Case, right? when the Navier-Stokes solver is cheap, this tau c will be very small. So in that case, it might be that everything is dominated by this tau f, r, and p. Especially this f includes noise filtering. So I don't know what you use for noise filtering, but if you want to use a good filtering algorithm with a good signal to noise ratio, then it could be more expensive. So everything would be dominated by this tau f in that case.
Yeah. We want to make the simulation cost is dominant by the tau f. If this is dominated by the tau f, actually you can see this tau f can cancel each other. So then the domination is the simulation speed up is only determined by the n and how many iterations you need to do. Okay, so the main purpose is we are trying to reduce the serial part cost, because this is you times the n, right? If this cost is significant, then you times the n, because you are trying to use more and more n. Right? We can consider k K is determine how accurate of your prediction, right? You cannot change the K if you have a predictor solver, but you can change N. You can increase the N so that you have better speed up. But if you have this term, it's also significant. You have N times here. The actually you increase N, the efficiency is not that good. But if you can consider this is small, okay? So then this speed up is dominated by the N. N is the number of subdomain. So this means if you can choose the two solver, certify the tau C is very small, and the communication does not cost much. You can speed up significantly just by increase the number of N. You have more and more N, and your speed up is just get better and better speed up.
Okay, thanks for the explanation. I think there's another question.
Okay, thank you, Pete.
Hi, Tim. Very nice talk.
Hi, Tim.
Yeah, I have maybe two questions. They are related. I think you talk about this parallel in time, but I think it's also very important you find a cost-grained model. Otherwise, like if you have like a small scale model, your time step is determined by your like some vibration frequency, the stiffness inside your system, right?
Yeah.
So it's not only purely time acceleration. You also need to find the spatial-wise how to get like a larger scale, a higher scale, like in the space, right?
Yeah, you need a cost solver, or you even for example, for the fluid problem, we just use the mean field solver.
Yeah.
So mean field solver actually you can consider is a kind of a mean field average of the DBT solver. So you can also use that if you have, for example, molecular dynamic simulation, you can use the cost graining system. For example, you can use the DBT system to drive the MD system. And if you have a quantum mechanics, you can use the MD to drive the quantum calculation. So this means you are trying to use a cost solver. It's much cheaper than your true solver. And what your purpose is to get the solution for the true solver, right?
But my question is that for the fluid mechanics, or for the like problem, you kind of have a good model in general, like across different scale. Then it's relatively easier for you to find the coarser scale model. If we have a coupling problem, if like you have a solid inside your fluid or some other like situation, and there may be multiple time scale you need to consider. And my question is that do you have some like a strategy to identify the proper coarser scale model for a given like a system?
So this will be problem dependent, as long as I'm not sure if you're talking about some specific system, then you need to currently consider how you can find a cost solver or give you the initial condition you need. As long as you can use the solution from the cost solver to initialize your fine solver, then you are fine with that.
Right, I understand, but sometimes finding the cost model, maybe it's not easy.
Yeah, it's true. It's some kind of sometimes you can find a good mean field solver or cost graining solver.
Yeah.
Sometimes if you cannot find, then you cannot use this kind of strategy to speed up your simulation. So that the only thing here is consider is if you can use the cost solver to reinitialize your system. So every time you have a cost solver solution, as long as you can use that, you get enough information from the cost solver to initialize your fine solver, then you're fine with that. you can
Sure,
definitely
sure. Yeah.
use the method. But if
Okay.
you say I don't have a code solver, then then we can not use this at all because you don't know the initial condition, right?
So kind of machine learning, like a pin can be a code solver. You can be developed.
Yeah. We are actually working. We are trying to use the pin as a surrogate model to do the prediction for the numerical solver, because if we train a neural network as a surrogate model, this can give very good. We do not say very good, maybe a rough prediction of the solution, and you can use that solution to initialize your system. So because after you train the neural network, the neural network will give you the solution instantaneously. So the time cost, again, we talk about the time cost for the tau C will be very small.
Okay. Another question. I think you mentioned there are many like advancement in the hardware, and I know that for MD, like DPD and many simulation, they are using explicit time step. I think now I wanted to hear your kind of thoughts about implicit solver for MD, for DPD or SPH for this kind of method. Then you can also increase your time step quite a lot. And maybe for some system, you can choose the partially interaction is implicit, like the very high stiffness part, and the relative low stiffness, nonlinear, you use explicit. And then I think you probably can increase your time step 1 or 2 order, probably, I guess. And but definitely you need also some modification. So compared to that direction of increasing time step and also your current method, what's your thought?
So just don't get rid of the power in time part. If you just consider the time integration part, even for the MD and the DPD, there is a different algorithm. They are trying to use the split algorithm. So they split the stiff iteration and the soft iteration into two kind of. You can consider when they solve the stiff part of the interaction, they are using the implicit integration method, and for the soft part, you just use a big time step to advance. So there's many different methods that are developed. They call this split algorithm. So they can split the stiff interaction and the soft interaction in two different parts, so that you can use a much larger time step to advance your system. This is another story. You can also definitely, if you have a good split algorithm, you can accelerate the simulation significantly.
Okay, thank you.
Yeah, thank you very much for all the questions. So in fact, I also have a lot of questions, but I would rather to keep it as a separate discussion after I read all your papers. And meanwhile, may I ask if you plan to upload this recorded video to YouTube channel?
Yes, I will leave a copy on YouTube.
That will be great. So our community can have other opportunity to rewatch. I mean, it's really worthwhile to watch it one more time to digest the information. But with that, I think for the sake of time, we maybe would like to close our today's seminar. And we really thank you our audience to participate today's discussion and the seminar. And let's also thank our speaker, Dr. Zhen Li, and also our organizer. And next week, we will have another interesting talk for this CFSM seminar series. So please schedule your calendar, and we look forward to see you next time.
Okay, thank you, Jiaoyan. Thank you all for